it means giving it agency. Right? So this combination of giving a machine agency and making it data efficient to build its own models and function in the world, when they crack that problem, I think it will change AI in it will be another phase change in what will happen. And I think that's coming.
But the reality is that this progression seems to have surprised everybody as to why it is going at such an exponential rate.
It's actually quite profound that the answer to the big question of who am I in the human context might actually come when we build machines that are able to do something similar. And then because we build them, we understand it better, and it might end up shedding light on what we are.
What causes that? Why is it that it is exploding at the pace at which it is exploding in terms of the ability of these models to do the tasks that we thought 18 months ago were simply not possible? Hi, everyone. This is the Tech Surge Deep Tech Podcast presented by Celesta Capital. Each episode, we spotlight issues and voices at the intersection of emerging technologies, company building, and venture investment. I am Sriram Viswanathan, founding managing partner at Celesta Capital. If you enjoy Tech Surge, now is a perfect time to hit the like and subscribe button. And while you're at it, you can leave us a review on your favorite podcast platform. If you're just discovering us, visit techsurgepodcast.com to sign up for our newsletter and check out the archive of some very interesting past episodes. We have a great episode this week where we trace the evolution of machine learning from its humble beginnings to the architectures fueling modern AI models like ChatGPT and others. We also explore ethical questions surrounding AI's rapid evolution and the implications of building machines that might one day mirror human cognition. Before we jump into this interview, I wanted to introduce a few key technical terms that will underpin our discussion throughout this podcast. Many of you in the AI space will be familiar with these concepts, which have defined the major inflection points in machine learning advancement. The first one is a concept called perceptron. This is the foundation of neural networks designed to classify data into distinct categories. Second, gradient descent, an optimization technique that fine-tunes AI models by minimizing prediction errors, similar to finding the lowest point in a valley if one were to traverse a side of a mountain or a hill. Backpropagation, a method that refines neural networks by adjusting parameters layer by layer to improve accuracy. Convolutional neural networks, or CNNs as they are called. This is the concept of key image recognition capability, enabling AI to detect patterns and objects in photographs or images. Transformers, the algorithm pioneered by Google and the architecture that large language models like GPT and others use, allowing machines to process vast amounts of data and understand context in language. Reinforcement learning and AGI, the frontier of AI, aiming to create systems that think, learn, and adapt, much like how humans do. Hopefully, we can demystify some of these complex AI concepts and make them accessible. Even if your last math class was in high school a while ago, whether you are a tech enthusiast, a curious learner, or just want a better understanding of the technology shaping our world today, we hope this conversation will help trace artificial intelligence's trajectory and appreciate some of its mathematical beauty and intricacies. So grab a drink or a coffee, sit back, and let's embark on this journey into the elegance behind modern machine intelligence with a conversation with Anil Ananthaswamy. Today, we have a very special guest, Anil Ananthaswamy, a good friend of mine from quite a while ago, who we just got connected more recently. But Anil is an award-winning journalist and a writer whose work delves into some of the deepest questions and fundamental truths we are grappling with in science and technology today. Anil is the author of several books, the latest of which is right here, which is Why Machines Learn, the elegant math behind modern AI. Anil, thank you for being here. It's really a pleasure to have you at this podcast.
Well, thank you, Sriram. It's my pleasure to be on this podcast.
So Anil, before it was just serendipity that you and I have known each other, and I last I saw you was at the TED Talk that you gave. This book, as we were just talking about prior to the podcast, you started writing it in 2020, almost prescient that you were talking about a topic that has become super hot right now and germane to all the technology buzz and excitement that is happening right now in AI and generative AI and AGI and all these models and all of that. But this book kind of attempts to sort of peel the onion on the underlying math and how it all comes together. And when I read this book, what became obvious to me is that the power of actually building something so sophisticated that we're all used to today, which almost feels like magic when you interface with GPT or Llama or any of these things, they're really built on some foundational, simple concepts in basic math that we all have sort of studied in high school math. So you say in this book that this book doesn't require a PhD in math, but it really requires a proficient understanding of basic math from high school. So perhaps that's a good place to start. What drove you to write this book, and what did you? What was the desire to go try to answer this question about machine learning and why machines learn, but really look at it from the math standpoint? Because I'm mindful of the fact that you started it before all this buzz started. So what drove you to do that in the first place?
You mentioned my other book, so I think maybe I can start by giving a little bit of background about how I even came to be thinking about writing about ML. I used to be a software engineer before I became a journalist, and when I was doing most of my journalism, it was about, like you said, particle physics, cosmology, even neuroscience, computational neuroscience, quantum mechanics, and when I write about those subjects and I interview the researchers and try to understand what they're doing, I don't really have any sort of ideas about doing that work myself. That's not my expertise, and I was perfectly happy writing about it. But somewhere around 2015, 2016, I started noticing that I was beginning to find more and more stories coming my way that had some component of machine learning. And so when I would interview the scientists, the computer scientists or whoever was doing the work, I think the software engineer in me got really intrigued. This was finally a topic where, I could get my hands dirty, so to say. I could do the software. I could understand what they were saying in a much more visceral sense because of my background. So somewhere the desire to, learn this technology, the nuts and bolts of this technology grew. And I got a wonderful opportunity in 2019 when I got a fellowship at MIT, the Knight Science Journalism Fellowship. And you have to do a project as part of that fellowship. And I basically proposed that I would, build some simple deep learning system. And I knew nothing about the topic. So I took that opportunity to go back to school, literally and figuratively. I ended up in...
You went to MIT.
So at MIT, the fellowship allows you to take classes at Harvard, at MIT, any number of classes that you want. So I was back sort of sitting in CS 101. I don't know if that's not the name of the course that they have, but you know what I'm talking about. Like literally sitting with teenagers learning about Python programming all over again. And then I slowly sort of bootstrapped myself and learned to implement some basic deep neural network stuff. Did my project. At that point, it was just mechanics. I was learning how to code. I could, code some simple stuff and make some things work. At some point, when I was learning the math, I started seeing some of the simplicity and the beauty of the math.
The elegance of it.
The elegance of it.
Yeah.
And elegance, of course, people are going to, argue about whether the math of machine learning is elegant or not. That's a subjective thing. I found it. Especially, there is I clearly remember the moment when I felt like, I wanted to write something along these lines, was when I encountered something called the perceptron convergence proof. The perceptron
Rosenblatt proof.
Right. So Frank Rosenblatt had designed the perceptron in the late 1950s. And it was a very simple algorithm. It was a single layer neural network, and it could, given two kinds of data, if they are linearly separable in some space, it could find the boundary that divides in finite time. The algorithm was very simple, but if you just looked at the algorithm, there was no reason to. The algorithm itself didn't tell you why this thing would work, right? And soon after the algorithm was developed, people started coming up with mathematical proofs of why this thing would work. And not only would it work, but it was a guaranteed, the proof guaranteed that the algorithm would find a solution if one existed in finite time. This is a pretty big deal in computer science, that anytime you can set bounds on your algorithm and definitively say something about what it's going to do.
If I may interject, I just want to make sure we're grounding ourselves here, because you're using a bunch of terms with a lot of our audience may not really fully appreciate. So before we get into the specifics of the algorithm itself, if you can just back up for a second and tell us, when you wrote this book, when you titled it as Why Machines Learn versus How Machines Learn, there's obviously a distinction.
Yes.
Why did you choose this title versus not how?
It ties in with this story that I'm telling you, which is that how to me is the algorithm, right?
How is the algorithm?
So if you look at the perceptron algorithm, it just tells you how that thing works, right? It doesn't tell you the rationale. It doesn't reveal the rationale for why it should work.
Yeah.
And the why is hidden in the math.
Yeah.
Right. So when you look at the proof, and it's a very simple proof that just requires basic understanding of vectors and matrices.
Yeah.
Basic linear algebra. And suddenly you have this amazing proof that tells you why this thing should work.
Which basically classifies a bunch of unstructured data into two categories based on some parameters.
Let's say you have data that belongs to two categories: images of dogs and images of cats. Right. And in some mathematical space, they occupy different regions of that mathematical space, such that there is a clear boundary between the two.
Yeah.
This algorithm will find a clear boundary. It doesn't guarantee it will find the optimal boundary, but it will find one boundary of the many that exist. And it was when I looked at that proof, that was what made me feel like, I would love to explain this to my readers.
But Rosenblatt, who's arguably sort of the starting point of modern day sort of machine learning, there are lots of things that have happened, after that has sort of transitioned the sophistication of the math and the sophistication of the learning algorithms to result in GPT-4 or DeepSeek today. But if you go back even before, maybe the early 60s, I mean, there was lots of work on AI, or what people thought it was AI, happened. But there were some seminal things that changed. Can you talk about what was the thing that changed the trajectory of the science and the evolution of the math and the way people understood the algorithm that changed this trajectory? Or was there one?
There was no single. I mean, you can always pick a single thread through this storyline, and one obvious thread to pick at is the story that relates to how neural networks work, developed. But machine learning is not just neural networks, and that I think is part of the bigger story about machine learning. Is that when Rosenblatt kind of designed his perceptron algorithm, that was a single layer neural network. It only had a single layer of artificial neurons.
Right.
An artificial neuron is simply a computational unit. Takes in inputs, does some computation, produces an output, right? And in Rosenblatt's perceptron, you could just have one layer such that the inputs were coming in and the output was being collected on the other side.
And the inputs being unstructured dogs and cats, and output being
some
a segregated classification of these two things.
So the input could be, if you had a 10 by 10 image of a dog or a 10 by 10 image of a cat, you would turn each pixel of that image into an input. So there'll be 10 by 10, so 100 inputs coming in to the single layer. And on the output side, you would have the network telling you, oh, 0 for cat and 1 for dog, or something like that. Something very, very straightforward. But at the time, people didn't know how to train a network that had more than one layer. So the moment you put in another layer between the input and output, the algorithm that Rosenblatt had didn't work. And they didn't know how to do that at that point.
And that's when they gave up. Was that the lull period of the early AI?
Yes. So the late 60s, there was a very, very influential and seminal book published by Marvin Minsky and Seymour Papert. In fact, it was called Perceptrons, in honor of Rosenblatt's perceptron. And in that book, I mean, it's a heavily mathematical book, big tome, wonderful piece of work. And they, for instance, in that book, they have one of the most elegant proofs of why the perceptron should converge upon a solution. Right? But they also had another proof, which was that the moment you gave the perceptron a problem which was very, very simple problem, it was called the XOR problem. But the general idea is if the two categories of data are not linearly separable, which means that there is no straight line that you can draw between the two clusters. Then this algorithm,
fails.
And they proved it mathematically, right? And they took a very simple case of that kind of non-linear problem to show that even this simple thing can't be solved
with a single layer.
So
with great additional layers, you can sort of fit the curve between the two categories.
Except what Marvin Minsky and Seymour Papert did was they kind of insinuated, without proving, that multi-layer networks will also not be able to solve the problem. Right? So no one proved it mathematically. It was just by kind of association that, because a single layer network couldn't solve it, maybe the multi-layer ones could also not solve that problem. But there was no proof. But that was enough for a lot of people to become extremely skeptical of the neural network agenda. Right? So late 60s, early 70s, interest in neural network research dropped. So that was kind of, an AI winter, so to say. People stopped working on it. But there was other stuff going on. People were like, for instance, there's an algorithm called the K nearest neighbor algorithm, right? Which almost anyone who's done machine learning will encounter that as one of the first simplest algorithms that you can design. And that was developed, and that was also around that time, mid 60s, late 60s. There was a lot of work that was done with sort of, Bayesian classifiers. So, a lot of work going on with optimal Bayes, naive Bayes classifiers. And even this thing of wanting, like I said earlier, that Rosenblatt's perceptron finds some boundary between two clusters of data. It won't find the most optimal one. So people are also trying to figure out how to design optimal classifiers, right? There's a way in which you can divide two clusters of data such that the prediction that you make based on the answer you find will be minimizing the error you make. Because no matter what solution you come up with, there's always a chance of error that you might end up misclassifying the new data as this or that. And how do you minimize that, right? And so there was a lot of that work going on. But some people had not given up on neural networks. Probably the biggest name that now is a big name, but not then. He hadn't. Jeff Hinton, right? So he was doing his PhD at that time in the late 60s, early 70s. And he was convinced that neural networks were going to be important. And yet we didn't have a way to train multi-layer neural networks.
So Rosenblatt comes up with the single layer perceptron neural network algorithm.
Right.
And then they realize that the more number of layers creates a way for the prediction accuracy to improve. And Hinton comes and says there's a way to actually implement this concept called backpropagation. So that makes a big difference in how these algorithms become capable of doing more machine learning. So can you talk about what is the fundamental aha that Hinton was able to do, enhancing what the original Rosenblatt concept was?
So I think we should probably, before going to Hinton, we should mention another seminal neural network result that was also in the late 50s, right? It happened here in Stanford. And this was Bernie Widrow and Ted Hoff.
Ted Hoff of the Intel fame.
Ted Hoff, yeah. So there's this wonderful story about how Ted Hoff was looking for an advisor for his thesis. He comes knocking on Bernie Widrow's door one afternoon. This is Friday afternoon, and he comes in, this young kid, and Widrow basically starts explaining some of his work to tell him that maybe this is the research we could do. And in the course of that discussion, this is just a preliminary discussion, and a potential advisor and a potential grad student are having. They design this thing called the least mean squares algorithm,
LMS.
And it turns out, and I interviewed Bernie Widrow. He must have been in his late 80s, early 90s then. He's still around, amazing man. And he recalled that moment and was telling me that, I wish I had a camera at that point to take a shot of what we wrote on the blackboard, because I felt like we had discovered the answer to life and everything. It was like this. It turns out that the algorithm that they had invented is a very, very noisy form of something called gradient descent.
Yeah.
And gradient descent is the central thing that is being used to train neural networks today. And they had figured out, without using calculus, just algebra, a very noisy version of that algorithm. And they did this on a Friday evening. They wanted to build it in hardware. The Stanford supply room was closed, so they go to the nearest hardware shop, buy all the things that they want. Over the weekend, they basically solder all the stuff together, and by Monday morning, they have the world's first functioning single layer, single artificial neuron in hardware, working on their desk, right? And the LMS algorithm is actually the true precursor to the backpropagation algorithm that you mentioned that Hinton had. Hinton's name is attached to. Backpropagation, the idea of backpropagation, and I'll explain that in a minute, but it's, Hinton's name is associated with it today, but actually that, even he will acknowledge that there were other people before him who had worked out various parts of that, including his postdoc advisor, Rumelhart, who was, if he had been alive today, he died early at a very young age. But if he had been alive, I think he would be, legitimately feted for the backpropagation algorithm. And Hinton would acknowledge that very much so.
I mean, just for the benefit of our audience, what currently exists as OpenAI, Ilya and others, actually came from Hinton's lab in University of Toronto.
Yeah.
So as you point out, the backpropagation was a seminal event that took the gradient descent algorithm, which built on the Rosenblatt perceptron. And there's a bunch of other things that happened, but I want to just sort of, pause here for a second on the gradient descent algorithm that you talk about. There's this one picture on your book, which all of us have seen. If you're flying over Asia, especially in Vietnam, you'll see these
rice paddy fields,
rice paddy terraced fields. And that is a physical representation of how the algorithm works. If you look at the farmers that are trying to go down to the bottom of the hill, can you talk about just the gradient descent? What is that algorithm?
Yeah, so the way to think about it is you've got some machine learning model that you're training. You provide it an input, it produces some output. Because in the beginning, the parameters of the model, whatever they are, we don't have to, because the model can be anything. It doesn't have to be a neural network. In the beginning, the model parameters are randomly initialized. You provide it an input, it produces some output. And if you're using this idea called supervised learning, where you actually have training data in the form of input-output pairs, where you have collected enough human labeled or human annotated data that tells you that for this output, for this input, I should get this output. So in the beginning, if it produces a wrong output, you calculate the error that it makes, which is the difference between what it predicts versus what it ought to have predicted, right? The error that it makes. And if you formulate that error in terms of the parameters of the model, you can, in some instances, you can get a function that is bowl-shaped.
Yeah.
Right? The error function is bowl-shaped.
Yeah.
Right? Not always, but it's especially in neural networks.
It's a three-dimensional, paraboloid,
if,
whatever.
If it is just two parameters, then
It's a parabola.
then it will be a paraboloid, right? So when it makes an error, essentially what happens is you situate yourself somewhere high up on that paraboloid. And gradient descent is simply this idea that at every point, at every instance when you've made an error, you calculate the slope of that curve, and you basically take a small step towards in the negative direction of the slope. So you're coming down to the bottom of the bowl.
So that you're minimizing the error rate.
Yeah.
So that by the time you're at the bottom of the bowl, at the lowest energy state,
yeah.
the model has given you the perfect prediction
yeah.
of what the output needs to be.
Yeah.
And conceivably, that makes a difference between the right answer versus a wrong answer that you might get.
Yes. Right? And this is what Bernie Widrow and Ted Hoff had figured out how to do algebraically. And it was a very noisy version. Noisy version simply meaning that when you're at some location on that surface of that, that curve, if you go down precisely along the gradient, you're doing exactly gradient descent. But if you just randomly kind of walk around, hoping to come down, like a drunkard's walk, eventually you'll come down to the bottom, but you can wander around a lot. And that's what a noisy version would be.
And this is the reason why this analogy that you had on the paddy fields makes sense. If you're trying to go down the paddy field the fastest way, you'll make these minor steps towards a
from
grade.
One terrace, you just look around what is the steepest, way down to the next terrace. So you go down, you wander around that terrace, find the next steepest path. And before you know, you're at the bottom of the valley.
Right.
So, and that's exactly what's happening in these algorithms, that you formulate your error in terms of the parameters of the model in such a way that the function hopefully has so-called a convex shape. It's kind of weird because convex we think of as being upside down like that.
Correct.
But for functions, convex means it's a bowl.
The other way around. It's a bowl.
So if it's a convex function, then if you can use gradient descent and be guaranteed that you will find what's called the global minimum, right? And that's it. I mean, literally, that is the basis of.
And how does that go from there to Hinton's work on backpropagation? Because that's sort of the precursor to where Hinton led.
Right. So this algorithm we are saying works really well if you have just a single layer and you can formulate it. But the moment you put another layer between the input and the output, it was really hard to figure out how to formulate you have to propagate your gradient from the outermost layer back towards the input layers.
I see.
And they hadn't quite figured out how to do that. So essentially, when you make an error, you have to assign blame for each of the model's parameters, saying each of the model parameters is responsible for this much of the error. This idea was there. This idea was there in the 60s. People doing research in rocketry, like control systems for controlling rockets in space. They had some version of this idea in their algorithms. There were people in economics and other places who were kind of grappling with this issue, because this is not just about training neural networks. It's about any model that you're building where you might have this issue. So people had sort of grappled with various versions of this. Rumelhart, Hinton, and Williams, when they wrote their 1986 Nature paper, they were the first to very clearly show how to use this idea for training so-called deep neural networks. Neural networks with one or more hidden layers between the output and input. And they were the first to also show if you use this algorithm, which they call backpropagation, then what is it that the network learns? So they kind of really brought it all together to say, okay, this is how we train neural networks with more than one hidden layer. And that changed the game, right? I mean, that was a big inflection point. Until then, we didn't even know how to train these networks.
So this was a seminal moment of just improving the accuracy of the prediction. But then there was also other substantial advancements in the algorithms itself in terms of before even we got to transformers, the convolutional neural network happened.
Yeah.
So can you talk about, what led to that leap? So from backpropagation, they understood how to actually tweak the weights of the parameters to improve, as you said, the blame assignment, to improve the accuracy of the prediction. But then there was another evolution of that to the convolutional neural network. So just tie that back to us on how does that?
Yeah. So you're exactly right. I think so. The backpropagation algorithm was one inflection point which allowed them to make more accurate predictions, but also it changed the nature of the problems you could tackle. Right. Before multi-layer neural networks, you could only tackle so-called linear problems, and now suddenly you could find non-linear boundaries in order to separate or categorize data.
Like, what is an example?
Anytime you have, like for instance, just in 2 dimensions, if you have a bunch of data that's clustered around the origin, let's say circles, and then you have triangles that are scattered in an annular ring around the circles, and there's a gap between the two, and you want to find a curve that fits that gap. A single layer neural network will not find it because it can only find straight lines.
Right.
But with multi-layer neural networks, you can find that circle.
Yeah.
And then suddenly you're able to classify the inside. You're able to separate the inside from the outside.
So this is profound because one of our companies is a company called 5C, and another related company is a company called White Rabbit, and both of them are AI companies focused on detection of cancer, in mammograms.
Yeah.
So if you take a regular mammogram and you have an image, and if you want to predict if some part of that image resembles a tumor, what you just said is what enables that detection to become accurate by the use of this nonlinear thing.
Absolutely. So. And I would not be surprised if what those companies that you mentioned are using some form of convolutional neural networks or maybe even transformers today. But they are just, it's a progression that began with the ability to train multi-layer neural networks, right? So Hinton did that. And then somewhere in the 90s, Jan LeCun, who was working, who had independently kind of come up with a version of the backpropagation algorithm, and he got in touch with Hinton, and then came to work with Hinton in Toronto for a year, and then at that time figured out the convolutional neural network, the architecture, right?
So Jan LeCun is who currently is the head of Meta AI's AI work with Llama and all that.
Yeah.
So he is arguably the person that pushed the CNN.
Yeah. So the CNN really, again, there is a history there also. Right. There were other people, Japanese researchers, and there's this whole history of people who were messing with various aspects of it. And LeCun is credited with kind of putting it all together to demonstrate a working prototype of what's today called the LayNet. And it was one of the first real applications of the backpropagation algorithm to train this thing called a convolutional neural network. And a convolutional neural network is a particular way of arranging the model parameters so that you're able to. It's a way in which the interconnections of the neurons are arranged so that you're better able to pay attention to aspects of an image. Right. So you, for instance, one of the things you want to do when you're trying to do image recognition or anything to do with images is have something called translation invariance, right? Where if you have an edge that you want to detect, right, you should be able to detect that edge no matter where it is in the image.
Whichever shape it is in, whichever orientation it is in.
So the orientation is rotational invariance.
Right.
But translation invariance is just if you're moving it in one
space,
axis, along one axis, right?
Yeah.
So, and the CNN allows you to architect the structure of your neural network in a way that it has rotational invariance, it has translational invariance.
Yeah.
And then also, once you detect edges or curves, etc., then you want to be able to compose those things.
Yeah.
So let's say you're trying to recognize a cylinder, Now a cylinder is going to have straight lines, but it's also going to have some curves. So the first layers will recognize the basic features, the edges and the curves. The second layers, higher layers will start composing them to start recognizing more complex shapes. And before you know, it has recognized a cylinder. So, and you can think of how something like that would work in the context of a dog or a cat, right? You're trying to recognize edges and curves, etc., and then you start putting all those together, and before you know, in the higher layers, you have recognized a cat or a dog.
So this is a good point to sort of touch on. So Fei-Fei Li's work in Stanford and ImageNet played a big role because they were almost, in a parallel universe. They were trying to solve image recognition using some of these early techniques, and they had tons of data. So can you talk about how the availability of this large data set actually pushed the envelope on just fine-tuning this whole recognition problem?
There was a fair gap between Jan LeCun's early convolutional neural network work and Fei-Fei Li's work, which then led to Hinton and Ilya Sutskever and Alex Krzyzewski's AlexNet, right? So let me just give a bit, your listeners a bit of an idea of what happened in between, because that's actually very amazing time in machine learning, which was, Jan LeCun, creates his convolutional neural network, but it didn't take off in the industry, mainly because even he knew that neural networks required a lot of data to train. They were data hungry things and also computationally intensive. So while he had created the convolutional neural network, it was a very bespoke sort of implementation. And also LeCun and his colleague, I forget his name, but they had come up with a framework for implementing neural networks, but that framework was not open source. It was proprietary. And so anyone else who would want to implement a neural network would literally have to do a PhD project all over again. And so that kind of...
It's ironic that Llama is now led by Jan LeCun, who's like the godfather of open source.
Yeah, probably because of lessons learned from that time, right? And so there were two things. One, it was not openly accessible, the framework. And the other thing was it was extremely data hungry. So people didn't really think it was going to be very useful because there was no such data available to train these networks. So early 90s, another big development happened in machine learning, which was the development of these things called support vector machines.
Yeah, SVMs.
SVMs just took off. They were very, very good at working with low amounts of data. And remember we talked about Rosenblatt's linear classifier, which was a perceptron, and it found a classification boundary between two clusters of data. And it was not guaranteed to find the optimal boundary. Support vector machines find an optimal boundary, but then they use something really amazing. And one of the mathematical pieces in the book that I find to be the most elegant is this idea of taking data that is in low dimensions, which may not have a linear boundary to separate the two. You push that data into high dimensions, and in some respectively higher dimension, that data linearly separates into.
So just give us a sense for in practical terms. I mean, I can understand you have a bunch of unstructured data set, which let's say comprises of cats and dogs in the data set, and you have a linear separation that you can do with what Rosenblatt predicted.
Yeah, but the thing is that with the perceptron, if the image is complex enough, right? Let's say cats and dogs, and if you just turn the entire image into a long vector where if it's a million pixel image, maybe not a million is too much. Let's say 1,000 pixel image, right? You turn that into one long vector, which is 1,000 pixels lined up, and you feed that into your neural network, and it has to classify that as 0 or 1, depending on whether it's a cat or a dog. In 1,000-dimensional space, the images of cats and dogs may not separate cleanly.
Accurately.
Yeah, they may not separate cleanly in the sense that you could not possibly draw a hyperplane to separate the two, right? So perceptron won't work.
Yeah.
And that's when you need to project this data into
Higher dimensional space.
from 1,000-dimensional space to million-dimensional space.
So that's where SVMs or support vector
kernel methods. So support vector machines, what they do is, if you have a boundary between two sets of data, they will find a classifier that is centered really in between the two, so that when you then do predictions, you're more likely to be right.
Yeah.
Right? But if you give a support vector machine unstructured data that is not linearly separable, it will also fail.
Yeah.
But what they did was they combined support vector machines with this amazing idea called kernel methods.
Yeah.
Kernel methods, what they do is they project the data from, let's say, 1,000 dimensions into 1,000,000 dimensions.
Yeah.
In the 1,000,000 dimensions, there is a space between the two. So the SVM gets to work, right? And then you project it back. And when you project that SVM boundary back into 1,000 dimensions, you will find it's a nonlinear curve, right? The really important, amazing part about kernel methods is that in order for the SVMs to work, they have to do some linear algebra of the data using the data points. So if in 1,000 dimensions it costs you a certain amount of computation, if you move the data to 1,000,000 dimensions, it's going to just blow up the amount of computation you need to do.
So the idea would have to be then the computation happens at the lowest dimension or the lowest layer.
Yeah.
And then it abstracts it away and you get the accuracy at the highest level. But the low energy state is where the actual computation happens.
So, exactly. So kernel methods, what they do is they allow you to project the data into high dimensions, but they do the computation in the lower dimensions.
Yeah.
So the computational cost is
much lower
of the whatever you were doing in 1,000-dimensional space. But the actual effect of the computation is as if you had done the computation in the 1,000,000-dimensional space, right? And that became a big deal throughout the sort of late 90s and early 2000s. Support vector machines were ruling the roost in terms of machine learning.
Yeah.
So if you look at if you talk to industry veterans, they'll tell you that so much of the machine learning work at that time was support vector machines and kernel methods combined. Right? So then what you were referring to earlier with Fei-Fei Li's, so Fei-Fei Li started this project of saying, okay, we need good data.
Fei-Fei Li is the ImageNet professor at Stanford
who started the ImageNet
project. Yeah.
So ImageNet project was this gigantic effort to create a data set of images that then could be used for image recognition challenges. Right? They literally created the largest curated data set of images at that point, and it was a very big deal because
this involved having to actually take an image, do the tagging, and then train the algorithm to actually be able to recognize.
Yeah, so they were not. So they were at that point not. The ImageNet project itself is just creating the data set. Right. So then it was open for others to then use that data set to train their classifiers.
Yeah.
And it became part of a contest, the ImageNet image recognition contest, right? And in the first year or two of that contest, neural networks were not in the picture, right? There were standard sort of ideas in image recognition that were, again, winning that competition. And 2011 was when we saw, I think it was 2011 or 2012 that the team led by Hinton, Ilya, and Krzyzewski, they created AlexNet.
Yeah.
And that was the inflection point. So there were two things that happened at that point that made it possible for AlexNet to win the competition. One was the availability of the data that was provided by ImageNet. Right? The other was the use of GPUs.
Yeah.
They were amongst the first teams who recognized that we can use these GPUs, which were actually manufactured for some completely different purpose, right? That they could co-opt these GPUs for training deep neural networks.
So I want to put a pause on that because I think this is an important point you're bringing up, because I think you've sort of laid out the early history of the development. There are still a few other key inflections that happen, including the 2018 transformer neural network that happened with Google. But before we talk about that, each one of these things that have actually contributed to the evolution of this area have made incremental progress. But what has happened is that you alluded to Ted Hoff in the early days. Who was an Intel guy who did the early you fast forward all the way, and then you made the comment about GPU. That's a big leap from Intel as a compute CPU related engine to then finding NVIDIA, which actually makes GPU becoming a much better targeted platform to do all of this work. Just bridge that for us. What made that change for a GPU to be a more ideal compute platform for this kind of algorithmic work, or not a traditional, CF transistors, billions of transistors, CPU? Why couldn't a CPU be used?
Right. So this is why I think the math of machine learning is so amazing, right? I mean, so it's all tied to the way the math works. If you think of what a neural network is doing, forgetting for a moment non-linear issues, etc., you have input coming in, which is just a string of numbers. Any data that you have, whether it's text or images or audio, can be converted into a vector. Right? The vector comes in, and on the output side, you might be asking for another image, another snippet of audio, or just one number saying something is 0 or 1, like a dog or a cat, whatever, doesn't matter. So on the output side also, you have a vector. The vector could have just one number or a million numbers to represent an image. So you have a vector coming in on the input side, a vector coming out on the output side. In the middle is a huge matrix. You can think of your entire model as being this huge matrix that just multiplies the input vector and turns it into an output vector. Right? It's implementing some function.
Usually it's a sparse matrix.
Could be. Depends on the data and depends on the architecture of your, neural. If it's a neural network, then it can be densely. It depends on the problem and the data. But generally, there's a matrix in the middle, and it turns out that GPUs, which were essentially built to update a matrix of numbers, which are the pixels of an image. I mean, they were gaming engines, right? So they were really, really optimized to do fast calculations to update a matrix of pixel values.
A scene in a game.
Yeah, anything. It's just screen, right? You're updating your, video screen at a very fast refresh rate. And so they were really good at crunching numbers so that they could update this matrix of numbers. And it was sitting right there. It wasn't designed for machine learning, but the underlying hardware was very, very good at exactly this kind of linear transformations that you needed to do. And so teams recognized that. Hinton's team, in particular, Alice Krzyzewski, who was a whiz kid with programming GPUs.
Famous for AlexNet.
And AlexNet is named after him. Right? And Ilya was the guy who saw the potential. He was the guy who convinced Hinton that, look, I think we need to do this because it will happen. That we will be able to crack this problem if we put enough compute on it. Right? And build a deep neural.
And this was the early. It was not even the H100s, I assume. It's like the early NVIDIA chips that were being used for gaming. That they used.
Machine learning was nowhere in sight with regards to these GPUs, right? It was not designed particularly or optimized particularly for these things. So
let's just fast forward from there to the transformer, because that's another big evolution in the nature of the algorithm that has changed the way what we currently use in GPT is it's a transformer algorithm. So talk about that.
So again, maybe for context, let me give a little bit of the connecting dots so that why the transformer came about will make sense, right? So we had AlexNet and other convolutional neural networks, and these were so-called feed-forward neural networks where the input comes in, the computation just proceeds in one direction, and the output comes out. There is no recurrence inside the networks, right? So the state of the output is not fed back somehow. But there were other things that were also happening in neural network design, which were called recurrent neural networks. In particular, there was something called long short-term memory networks, LSTMs, right? These were really being used for what transformers are being used for today. But when you go back to 2015, 2014, around that time, Google was using LSTMs for doing machine translation. So-called sequence-to-sequence transformation. You have a sequence of words in one language, let's say English, and it has to be translated into German, which is a sequence of words in a different language, and there is no one-to-one correspondence between the input word and the first position and the
lot of computation happening in the middle.
A lot of computation happening in the middle, and so the sequence is coming in one word at a time, and another sequence is coming out on the other output side one word at a time, and the sequence matters, right? And so the network has to remember what has come before up to a point, so that it can process, produce the right kind of output. So LSTMs were all the rage at that. They were, but they had limitations, right? You could only remember so much of the sequence that was coming in.
Right.
If the dependence of the language sentence that you were trying to translate was such that the 100th word dependent on the 10th word that you had produced, that much information was hard to keep, right? So it had inherent limitations, and also it was sequential. So there was a performance problem, right? It was not parallelized.
And computationally very expensive.
It was.
Yeah.
So 2017 was when the team at Google Research and Google Brain, there are 8 authors on that Attention is All You Need paper, who came up with the architecture which basically says that you can parallelize the entire operation of taking a certain set of input words, if it's a sequence of words, and then producing your output sequence, whatever that might be. So they did it for machine translation, right? That paper.
But the whole distinction there is really the parallelism that they were able to achieve versus the sequential nature of doing it with STSM before that.
Yeah. So essentially, what the transformer does is the way you can think about it is you start with a set of words, right? And these words have to be turned into vectors. So you embed them into some vector space so that they have some semantic meaning. And then you keep transforming those vectors layer by layer. And that's hence the name transformer.
Right.
And the transformation depends on what each word means to the other word. Yeah. So let's say a word in the 10th position relies on something that happened in the second position. So it's paying attention to and hence the word attention.
Yeah.
So different words are paying attention to different parts of the sentence. And you keep doing this layer by layer, and at the end of let's say a set of 10 transformer layers, you end up with a new set of vectors, embeddings, so to say. And now those things can be then turned into words. Right. And if you're doing sequence to sequence, where English to German, then the final thing, you would have to then add, it's a complicated architecture between, you have to encode it first and then decode it next. Right? But essentially, that's what it's doing. It's transforming your input vectors into some sort of new set of vectors that now contain the information necessary, the semantic information necessary to then decode it into any language you might want. So, but when the 2017 paper came out, they had done a very particular architecture which required you to encode your data first and then decode it to produce a new sequence. The stuff that happened with GPT, for instance, people realized that the same thing could be used for next token prediction or generating text, right? And so in this case, what you do is you start with the same thing. You start with some set of words, convert them into vectors, keep transforming those vectors so that you get a new set of vectors that now has all of the semantic information encoded in each position. The final one is your vector which is representing the one that you need to predict, that is supposed to follow. Let's say you had 10 words and you are trying to predict the 11th word. The 11th position will now, the vector that you end up with at the very end, will have all of the necessary information somehow because of the series of transformations, right? That you can say, oh, this is the most likely 11th word.
So this is absolutely remarkable, grounding, and I can talk to you for hours just delving into this topic. And but let's just try to converge this on some of the more recent sort of things that are being battled in the market. Clearly the transformer architecture is evolving, constrained only by the underlying compute power that you can throw at it. Mm-hmm. And as you put more compute power, and you can obviously pre-train a number of these models. We won't get into sort of the open model versus the closed model and all of that. But the reality is that this progression seems to have surprised everybody
Yes.
as to why it is going at such an exponential rate. You could, clearly, Moore's law, you could sort of talk about the compute power is growing at a dramatic scale.
Mm-hmm.
But that doesn't seem to be linearly translating to the improvements that we're seeing in the underlying model and the pre-training that has happened. And in fact, Sam Altman just this week says that it's actually the models are becoming more efficient, 1,200 times, almost every year. What causes that? Why is it that it is exploding at the pace at which it is exploding in terms of the ability of these models to do the tasks that we thought 18 months ago were simply not possible?
Yeah, I think the way to think about why this might be happening is to think about what the transformer is learning, right? So the transformer basically, every time you give it a set of words, it has to predict on the output side the most likely next word to follow, right? So let's say it has a vocabulary of 1,000 words, right? So for each of those 1,000 words, it has to predict the probability of what is the probability for word number 1, word number 2, all the way to word number 1,000, right? So if you look at the transformer as a black box, it's essentially a function that takes in a vector, which is your bunch of words, and on the output side produces a vector for one word,
right?
Which is basically the most likely next word. But inside it has to calculate something called the conditional probability distribution, right? Over its entire vocabulary. No matter what input you give it,
right,
it has to calculate this conditional probability distribution and then sample from it so that it takes the most likely next word and says, okay, here's your output. This thing that it has to do is an extremely high dimensional calculation. It's a calculation that is done in extremely high dimensions.
Right.
And high dimensional surfaces, when you're doing computations in high dimensions, you have this problem called curse of dimensionality. You really require a lot of data, and you have to estimate a very, very complex shape. So when the models were small and when the data was small, just 3 years ago, the shape of this probability distribution that had to be calculated was not very accurate. So the predictions were not accurate.
Right.
But as you started throwing compute and
more
data at it, it just became better and better at every conceivable sort of aspect of this probability distribution could be calculated.
Yeah.
Right. So mathematically, it's not a surprise
that the pace of improvement.
Well, the pace of improvement is more also a technological thing. They do all sorts of things to fine tune their models. But just in terms of sort of why putting sort of more compute in terms of taking more data and training the model, but also increasing the size of the model, because the more parameters you have, the better you're able to model this extremely complex high dimensional surface. Right. So mathematically, it's not a surprise that they're getting better, because the moment you can correctly estimate all of the conditional probability distributions, no matter what input you give, it can calculate the appropriate conditional probability distribution and then spit out the next word. Right? It's getting better at that. But what has been surprising is that that's all it's been trained to do. It's just been trained to do next token prediction, next word prediction. And despite that, because nowhere in the training regimen is there any idea of solving a problem or summarizing a text or any of these things.
Or writing poetry.
Whatever, nothing, right?
Yeah.
None of that stuff is there. So you take this base model, pre-trained model that only does next word prediction, and you can fine-tune it to do these amazing tasks just out of this very, very simple sounding training procedure. That has surprised people.
But is there an asymptotic sort of max or decay in this thing where it slows down?
Yes.
And why would it slow down? And
because
when does it slow down?
Because all curves that when in nature, when we see them rising exponentially, usually we are only seeing the part where they're rising. Eventually they tail off.
Right.
So it's always a S curve. It starts like that, goes up, and then ends up plateauing.
Right.
So we've already seen that happening with large language models. So a lot of the sort of scaling laws that were empirically figured out in 2021 applied to the pre-training part, the stuff that I just mentioned to you.
Yeah.
People already started seeing that the the sort of benefits that you were getting, law of diminishing returns was kicking in.
But is that largely because of the natural way these models are expected to do, or is it because of lack of data? Because one could argue you're running to the sort of the peak data problem of you don't have enough data. That's why you have synthetic data, right?
Yeah, I mean, all of those things will play into the lack of data, lack of good quality data. Synthetic data might end up skewing your model in a certain way because it depends on what is generating that synthetic data. So there are lots of issues there. You will essentially, in practical terms, that exponential curve was hitting a it was kind of saturating.
I see.
Right. So what has happened in the last 6 months has been very interesting, where instead of putting compute and data efforts on the pre-training, we have now shifted to providing more compute to the large language models on the inference side. So once you have a trained model, right? Before, what used to happen was once you have a trained model and you asked it a query, it would just generate a series of tokens, right, through many passes through the network, and those series of tokens translated into words represented your answer.
Yeah.
But if it had to do, if the question involved some sort of logic puzzle or quote unquote thinking,
or slow thinking,
it wasn't doing that. It was just producing that output. But now we have developed the ability where you spend more time generating, maybe different versions of the answer, or sifting through your different versions of the answer to find the right one. So you have moved the responsibility of how much compute you use to the inference side.
Yeah.
So there's more compute being expended on the inference side now, where the model spends more time generating a variety of tokens and potential chains of thought, so-called chains of thought, as it tries to answer that question.
Yeah.
And so the scaling law has shifted. So now we have entered the regime of a new scaling law, where putting more compute there might give better performance for another length of time.
But that leads to a good question, because I think you touched on Yann LeCun and Hinton. They're sort of cut from the same cloth, as it were. But the both of them have sort of diverged pretty dramatically in their beliefs around where this evolution is headed, especially in the context of AGI, where Hinton seems to be suggesting that this has to be reined in, otherwise it's really could be disastrous.
Yeah.
And Yann LeCun doesn't think that. So can you shed some light on what is the core thesis of the argument on the both sides?
So you're right. I think so. Of the so-called three godfathers of AI, Hinton, Yoshua Bengio, and Yann LeCun, Hinton and Bengio have become very, very concerned about how we're going to be able to rein in or make AI safe. They are afraid of sort of runaway processes where we may not be able to curb these AI, especially agentic AI. If we build autonomous, like right now, AIs are still kind of reactive. They are reacting to us, our prompts and our inputs. But agentic AI is coming, where we are building AIs to be autonomous. And I think Hinton and Bengio are concerned about where that is going, and they have been raising the alarm. Yann LeCun hasn't gone on the same path. He has, in fact, talked about how the current technology that we have, LLMs in particular, are not enough to get us to AGI. Right? He is very clear that we need other innovations that will make these AIs come close to what we call AGI, artificial general intelligence. And so he's both, I think, not concerned about the power of these systems, because he thinks, this is not the path to AGI. But also, I think he has a different view of how safety, like he doesn't want to worry about safety until we have built that thing. It's like saying, we anticipate a technology that we haven't yet developed. How are we going to design safety mechanisms when we don't even know what the design of that thing is that we are trying to aim for?
Yeah.
So he has a different approach. He's certainly less concerned about that than Hinton and Bengio.
Yeah.
And yeah, you're right. I think it's very interesting to watch how they have diverged in their opinions.
Yeah.
I don't know, the inner workings of their minds as to why they have taken these positions, but out, in their public pronouncements, you can clearly see this difference.
So one of them is right. I don't see a scenario
it,
where both of them are right, obviously.
No, it could be that both of them could be right in the sense that we may get these breakthroughs that Jan LeCun is talking about that makes these AIs truly more AGI-like. I don't think, AGI in its purest form is probably very far away, but we're going to get very powerful systems, especially when we make them autonomous. And it doesn't take too much for things to go wrong once you make things autonomous. So I think both of them, we might end up with some mix of the two concerns, right? So we'll see.
So let's reel this back in. I want to sort of, the last section, I want to just touch on some of your other books that you've sort of so wonderfully gotten into, comes from physics and some of these other areas that you've got. There seems to be a common thread, and I'm trying to figure out, other than saying that everything that you write about, I find fascinating, and I if I was not doing my day job, I would be following you around and trying to figure out how you think about things and how you learn and write, because it's really fascinating. So is there a common thread that drives you to write these sorts of topics and problem statements?
Deep curiosity and, utter fascination with the natural world.
Yeah.
Right. I think so. If there is a common thread, it's just that these books are all sort of looking at issues that are of, very deep concern to humanity. Right. Like on one hand, the first book, The Edge of Physics, was about cosmology, and it's about the universe. How did this universe come to be from a physics perspective? The Man Who Wasn't There it's about the nature of the human self. Like, who am I? And that's a question we ask ourselves all the time.
I had a little bit of a spiritual tilt to it in the way you told the story on that book.
Yes and no, in the sense that I kind of deliberately stayed away from religion.
Right.
I
said spiritual. I didn't say
yeah.
religion.
So yes, theology has had a lot to say about this question, right? Especially, actually, all theologies have attempted some form of an answer to the question, "Who am I?" So, in the epilogue of the book, I do kind of touch upon that, and in the prologue. But the core of the book is about the science of this question. Right? It's about neuroscience, neuropsychology. It's looking at the ways in which the self comes apart in a condition like, let's say, schizophrenia or Alzheimer's, and they all disrupt ourselves in different ways. So by looking at the different ways in which we come apart, the book has a thesis about how we might be put together by the brain and body.
But these are all key issues that one would have to grapple with as we try to build a AGI system, because a lot of how we think about ourselves and how we learn and how we interpret the real world is going to get replicated in some form in the systems that we build.
Yes, especially if we have to build AIs that are not as data hungry as they are right now.
Yeah.
Like humans are consuming nowhere close to the kind of data that AI is required to learn. So there is something about the way our brains work that is very, very efficient in terms of the way it models the world outside, how it can predict and act in the world. So if we are going to come up with, and how we even deal with the world symbolically, right? The way we reason. So there is still something lacking in modern machine learning systems. And if we are to get closer and closer to the way humans function, then most likely we are going to replicate some of these processes. We're going to end up with machines that have a sense of being a machine and giving them the agency to go and explore their world and in a kind of data efficient manner similar to humans. If that happens, these are questions that are going to need to be answered, and it's actually quite profound that the answer to the big question of who am I in the human context might actually come when we build machines that are able to do something similar, and then because we build them, we understand it better, and it might end up shedding light on what we are.
It's more analysis of, it's almost self-reflection on how we think about ourselves as we build these complex systems. If you had a crystal ball and if you were to look in the next 5 to 10 years, where do you think, based on your research, looking at the last 50, 60 years of all these key disruptions and innovations that have happened, where are the areas that you think, substantial sort of, nonlinear, disruptions are likely to occur? I mean, I'm not, it's not about, going from traditional CMOS or silicon to quantum computing or any of that, but in terms of the software and the machine learning, algorithmic work and all of that, are there one or two areas that you think are hard nuts to crack that might fundamentally change the area?
I think so. I think there's neuroscience has a certain way of explaining and understanding how our brains work, and there is a sort of dominant paradigm now that basically tells us that the way our brains work is by creating internal models of the world outside, and every time we have incoming information, the brain is basically using its internal models to predict what might be the external causes of that information. So if there's light falling on your eyes, it's not like the brain is basically constructing everything from bottom up, saying detecting edges and curves and colors and shapes, and then suddenly, aha, I'm looking at a dog. It's more likely that what the brain is doing, that it already has constructed internal models of what a dog might be like, and it's predicting that, okay, the light that's falling on your eyes is most likely because of this thing that is outside, right? So there is kind of a reversal of the processing that we traditionally think of as happening. And this idea that control systems like our brains have to actually build models of the world outside with suitable abstractions and situate themselves, like the agents, as selves within that world model, and then use all of that to navigate and do whatever humans do. I think when the AI folks crack that problem, like how do you let a machine do exactly that? Like navigate its world, build a model of its environment, situate itself within that model as being a machine in that model.
Yeah.
And do so in a data efficient manner where it's not asking for more and more data, but is very selective about what data it looks for and uses that to fine tune its own models. It means giving it agency.
Yeah.
Right. So this combination of giving a machine agency and making it data efficient to build its own models and function in the world, when they crack that problem, I think it will change AI in it will be another phase change in what will happen. And I think that's coming.
Would you say, is it 3 years, 5 years, 10 years?
Oh, that I don't want to.
Some argue that AGI could be in 2027.
So there could be extremely intelligent systems that are just reactive things, right? I mean, like an LLM is, no one is going to argue that an LLM doesn't have some kind of intelligence. Of course,
but no agency.
We haven't built that into them, but that's what agentic AI is beginning to do, where you have these external scaffoldings around LLMs that are going to act like agentic things. To me, those are still patchwork things. Right? If you can figure out, like when you think of the human brain, this is one single unit, right? And this has evolved by itself over 500 million years of evolution of the nervous system. This nervous system has figured out what it needs to do in order for this body and brain to survive, right? Nobody has been training this outside of itself. I mean, nature is doing this on its own. No in principle reason that a machine, we can't figure out what that algorithmic process is that will get machines to this point.
Yeah.
Except that we don't quite know what those answers are, right? So, in some level, in some way of thinking, these machines that we are building, these machines that we are trying to imagine, is also evolution in action.
Yeah, that's for sure. Well, Anil, this has been just remarkably fascinating for me personally. I don't know, as I said early on in this podcast, we can talk about so many topics and sub-trees within this general area. But thank you so much for just giving us a glimpse of the way you think about it and what you have tried to capture in this current book, Why Machines Learn. For our audience, I think if you are even slightly curious and technically open to sort of delving into your high school, early math and areas of that nature, you will find this book absolutely fascinating, as you will some of the other books Anil has written. So thank you, Anil, for joining the podcast. It was truly a pleasure and honor to have you on this.
Thank you, Sriram, for having me. It was my pleasure entirely. Thank you.
Thank you. Thanks for tuning in to the Tech Surge podcast from Celesta Capital. If you enjoyed this episode, feel free to share it, subscribe, or leave us a review on your favorite podcast platform. We'll be back every 2 weeks with more insights and discussions on all things deep tech. Thank you very much. Bye for now.